Morning, guys. So we're going to continue our study. This is technically a chapter 3 lesson, although as you listen to this lesson here, you'll see us revisit the concept of atomic radius and ionization energy. Hopefully that'll help you as you prepare for your chapter 2 test anyways. So in this section here, we're interested in studying some what are called periodic trends. Remember, we had this notion here, if something is periodic, it's something that repeats. And basically what we're doing is we're figuring out, based on organizing the periodic table in this fashion, we're going to start off looking at physical characteristics that repeat first, and then in a couple lessons time, we're going to switch over to do the chemical properties that are also periodic, that also repeat because we've arranged them in this fashion. So today I'm hoping to do a couple periodic trends with you. We're going to look at the first trend, which is just metallic, whether things are metals or non-metals. We're going to get to the radius and ionization energy. We'll see if we get to electronegativity. So for these periodic trends here, remember yesterday I introduced to you the fundamental principles that we're going to use to actually explain most of these trends here. You'll notice that I've actually pulled out an excerpt here from your data booklet. It's laid out exactly the same way you do a periodic table, but you notice unlike section 6, section 9 actually lists for you the different sizes of the atoms. Yesterday we did this sort of in terms of the concept of Z effective and coulombs force. So if you remember from yesterday's lesson, hydrogen has one shell, lithium, although it does have two shells, effectively once you subtract off how much inner electron shells are screening and blocking out the nucleus, the effective charge of all of these, it was like everything here is solid plus 1. And yet, when you actually start going down the table, if you look at the atomic radius is put at the top of each element, you notice that it goes 32, 130, 160, 200. We're noticing the trend is the fact that the radius increases going downwards. Again, we'll flesh this out a little bit more below. But the radius here increases. That was not as much due to the Z effective. The Z effective was still plus 1 for everything. But in this case here, it was due to the fact that as you jump down a row, we're going to go from, say, energy level 1 to energy level 2 and 3. Every time I go down a row with that increase in energy level, I'm actually one more shell out than where I was to begin with. So the radius increasing has all to do with us having more shells. There's a lot of explanation style questions in this chapter here. Your explanations cannot be, oh, I've just memorized the bottom is bigger. Oh, it's because the radius increase is going down. That's not an explanation. Your explanation has to come down to the fact of, oh, it's because we have more shells. Having more shells, it's like we have more layers of onion. More layers actually start going further outwards, and that's why we're actually further out. Z effective actually becomes a more important concept along with coulombs force as you go across the periodic table. Let's imagine we're on row number 2 here. Lithium itself has 3 protons. As you go across, you just pick up protons. Remember, what I'm suggesting here is the core of it, the nucleus, actually does increase. We're getting a bigger and bigger proton. But remember, we're actually not measuring the size of the nucleus. We're actually measuring how much hold does that nucleus have on, say, the second shell. And in fact, as that center gets more and more positive, the effective charge goes from being plus 1, plus 2, because we're picking up extra protons, but those extra electrons are not screening each other out anymore. We actually get, as the nucleus increases, having the two shells actually gets closer and closer and closer and closer. We actually get a smaller and smaller radius, as tracked by these numbers here. We used to be about a 130, now we're 99, now 84. You notice that it's actually a notable difference. The core itself, the center, where the protons and the neutrons actually are, this is getting larger because I'm getting more protons and more neutrons as I step across. But at least all these elements that are all row 2 electrons, we're going to actually end up pulling in the shell here tighter. And when we do talk about atomic radius today, we actually are measuring the distance between the center and the outermost shell. It is a notable drop here. There are a few exceptions here and there. You'll notice going from fluorine, even though neon should have the highest effective charge in this row here, neon is ever so slightly bigger. You need to come up with some justification, probably with that added electron. There's extra electron repulsion. It makes it slightly bigger than the fluorine ion. So just prepare yourself for a lot of explanation style questions as we look through these periodic trends. So far we've seen here Z effective and Coulomb. We know that as the charge increases, Coulomb was this formula, F is KQ over R squared. The Q's are the sizes of the charges. As my Z effective goes up, as I gain protons, the force is going to be proportional to it. the more positive the center, the tighter hold I have, the tighter I can pull in these two shells, making my radius shrink. So again, your trend is going across. We would expect that the radius decreases. That's not a reason. If I just gave you, oh, choose calcium and choose selenium, who's smaller? You can't just say selenium because that side's smaller. You need to tell me here, we know the radius is smaller. Look at where they are on the periodic table. They're on the same row. So you would say here, they're the same row, meaning they're the same energy level, but selenium has a greater Z effective. Even after you subtract off any extra shielding electrons, especially these transition metals or inner orbitals, these are definitely all shielding electrons. They block out the valence electrons actually very well. We're going to see at the end of this chapter. But the whole notion here, calcium only has 20 protons. I think selenium has 34 protons. With that dramatic increase in protons, way more positive in the center, the Coulomb attraction says the force is stronger, the size is therefore smaller. So that's, again, what we're going to look into here. We're going to flesh out a little bit more of this atomic radius. And also, once you know about the radius becomes a nice justification for all other trends we talk about. We're going to definitely get to ionization energy, and maybe more so tomorrow we'll do electronegativity and electron affinity. One property just before we dive into radius a little bit more is the whole notion of metal and non-metal. We know our periodic table here. We have a stair step that's roughly that goes down dividing the metals and non-metals. Hopefully you know by now the ones on the left hand side, these ones here are called metals. You can list for me some common properties, like they're typically solids at room temperature, they're malleable, ductile, they're sort of flexible in that sort of nature there. But in this case here, not all metals are the same malleability. Not all metals are the same even conductivity. And in fact, the thing that actually makes you a metal, one job of a metal, especially when it reacts, is it likes losing electrons. It likes getting oxidized. For me to actually lose electrons, I can either take something like francium. Because of all my shells, I'm going to be a huge atom. As I go across, like we mentioned, the size actually starts shrinking. In which case do you think it's easier for me to lose electrons? Hopefully you said here the francium, the large element, because I'm large, the nucleus is actually having a really hard time hanging on to those electrons. You come in with a pair of tweezers, you're ripping off an electron that's so far away. A radius that's so far away means the force of attraction is much weaker, and that means this electron gets popped off quite a bit easier. So one property that's just sort of generic here, based on how we define metals on this side and we have non-metals on this side, we can talk about a property called metallicity, so how metallic something is, and basically you can put an arrow here that says the metallicness, metallic properties increase in that sort of diagonal downwards direction, because that's pointing towards the most metallic atom, which is francium. If you Wikipedia it for some reason inside our universe, you can only harness about hundreds or thousands of atoms of francium. You can't really collect a good sample of it, so sometimes they just defer to cesium. That's a much more commonly available alkali metal, and sometimes they actually just say cesium is the most metallic, but definitely the largest ones. Again, one of the properties is they lose electrons very well. We lose our metallic character, our metallic nature as you step across. That's why they call them transition metals. And obviously non-metals don't have those properties. They typically are either gases or liquids at room temperature. They typically are very brittle, although we don't have a very good intuitive understanding because they're gases. You can wave your hammer around the air, hitting the air. You're not going to feel the fragileness until you take that gas, let's say nitrogen in the air, we cool it down to liquid nitrogen, so we get a slurry of nitrogen, keep cooling it down until we actually get a solid of nitrogen. Once you have that solid, you take a hammer to it. Because there is no lattice structure, it basically fractures and cracks on you. So very, very fragile, very, very poor conductor, or you can say it's an insulator. So those are just some general properties for metals and non-metals as physical characteristics. What I want to do is I want to flesh out this whole notion of atomic radius again, and then use that radius as an explanation for ionization energy. We're going to come back to this other diagram here, also in your data booklet. You have the full data booklet for your test, and it actually will emphasize for you here, for this lesson here, ionization energy, we also see how the ionization energy changes as you go up and down and across periods. So with that as an introduction here, let's just go through some of these properties. So we talked about the metallic character already. You can title this section here periodic trends, like we did up above. These are all physical characteristics that we're dealing with first. The first one I want to deal with you again is this notion of atomic radius. Radii with the two i's at the end is just plural for radius. I just want to emphasize here, we know this. It's the radius of the atom. In this case here, it emphasizes the size of the atom. I want to emphasize here, this is the distance from the nucleus, from the center of any one of these atoms, to the valence shell, to the outermost shell for that particular element. Yes, even though every element has an infinite number of shells available, we only measure out to shells that actually currently have electrons occupied. Now we get into a little bit of a problem from our chapter 2 stuff. Because our orbitals are just regions of likelihood, they're sort of probability distributions. They're sort of the chance of you finding the electron is somewhere within this. Let's say it's a spherical orbital. Let's say it's a 1s orbital. We basically have to make an arbitrary decision. Well, how low does the probability get before we say, okay, stop. That's going to be the size of the atom. Because in fact, although I have the greatest chance of finding my electron somewhere in the sphere, there is the off chance that the electron actually might appear somewhere out here. So what percentage, what fraction do I say, okay, the orbital only measures out to here? It's not very well defined. What scientists have done is they try to say, well, because these orbitals are a little bit annoying, there are these probability distributions, there are those wave functions squared, okay? It's a probability distribution. Instead of actually trying to decide on some arbitrary, okay, we're only going to measure out to 95% chance, 97% chance, or whatever, what they do instead is they actually take a molecule. Let's say instead of taking just a single hydrogen atom and just asking you, well, what's the radius? What is the center to this outer shell, which is the first shell? They actually take a diatomic, which is actually an H2. Now, the nice thing about H2 here is we're going to do this bonding a lot more in the 4th chapter. But in this case here, we know that hydrogen has one proton. It's a little bit weird that the most stable hydrogen here actually has no neutrons. So one proton in the core, one proton in the core. We know both of them have a configuration of 1s1 and 1s1. S orbitals are spherical, so there's a sort of ball shape around these two centers here. Instead of this problem of, okay, well, how far out does a single orbital actually go? What I'm going to actually do is I'm going to take this diatomic. These guys always hang out together. And what I'm going to do is I'm going to actually measure where is this proton? How far away is it from the other proton? I'm going to forget about this whole orbital stuff and this whole probability distribution stuff because it's much easier to just say, okay, here's my nucleus and here's my center, and I can track that as a distance. Assuming now, depending on the actual diatomic, it's possible that the orbitals don't overlap, it's possible that they just touch, it's even possible that these orbitals actually cross over each other. That's going to cause some problems with the simplification, but we're just going to pretend that distance that I said between the two nuclei, this is called the internuclear distance. It is an imaginary axis, a line between, that's why we use the word inter, between the nuclei. I'm going to imagine that for all diatomics, that the overlap isn't very severe. I know I'm going to, depending on the diatomic, I'm going to be off by a little bit. But if it's not very severe, if these are two hard spheres and they were just side by side, I can sort of approximate, sometimes they call this the covalent radius, because this one here is a covalent bond. Covalent radius can be defined as half the internuclear distance. So you see, by actually measuring the actual nuclei that I can physically see and physically measure, I can avoid this problem, how far out until the probability drops off when I don't care about it anymore. So half the internuclear distance. Yes, it's true, not everything shows diatomics. Metals would be good examples of this. Metals do something called metallic bonding, but in the same way, when metals in the solid state, metals are also going to be sort of atoms that are side by side by side like that. Instead of trying to measure just the orbital for one single atom, I can try to measure this internuclear distance, the distance between one center and another center, and then by approximating, let's just take half of it, that's going to be the radius. So that's going to be atomic radius. All that background, all we're just saying here is this is the size of the atom. And by extension in this section here, we're going to look at ionic radius as well. The radius of the ion, exactly the same definition, although for the ion, it may either have been oxidized, has lost electrons, lost electron shells, or it may have been negative charge, it's gained electrons and been reduced. So Again, what we're interested in here is the periodic trend. I already did this for you up above. So based on our periodic table, based on the way we organized it, we want to study the trends going up and down and the trends going left and right. We already saw, based on our numbers, the atoms generally get larger going down this way. If you need a reason for that, again, we're going to say the radius increases. We're going to use the terminology here, down a group. So we're going from top to bottom. A group is a vertical column. And basically what's going to happen here, usually we would rely on those principles Z effective as well as Coulomb force. But in this case, we saw, unfortunately, Z effective is going to be +1 for all of these. Once you subtract off all the screening electrons, the Z effective didn't change. I can even make a note of that here. Although the Zeph remains similar, let's just backtrack and let's just look at the Bohr model. As you go down, being down a row, the period number tells you your energy shell. Going down one row means you have another shell. Although Z effective remains similar, we have more shells. And more shells means larger. And that is your explanation. Not, oh, I just memorized the bottom is big. Okay? So that one there is good for an explanation going up and down. It doesn't have to necessarily be alkalis. It could be any elements. I could pick, let's say, fluorine, and I can ask you for, let's do iodine down here. I can ask you, which atom do you expect to be bigger? When you're framing your question, this is a nice tip when you do your test here. I know that fluorine only has 2 shells, right? So fluorine, 2 shells like that. Iodine, by the time you have your Bohr model, it's going to be 5 shells. I think 5 shells, yep. So 5 shells there. And because you have 5 shells here, as you're wording it, you can say iodine has a larger radius than fluorine, because I'm going to try to get you to avoid the term it, because I have no idea what you mean by it. Are you referring to the iodine or are you referring to the fluorine? So instead of using that pronoun it, I'd rather you just be redundant. You can say iodine has a larger radius than fluorine because iodine, just repeat which element you're specifically talking about. I think Englishly speaking, it actually refers to the closest article, which we don't want. In this case here, because iodine has more shells than fluorine. So be a little bit redundant, try to avoid that term it here. And in this case, you can even quote here, iodine has N equals 5 shells, whereas fluorine only has N equals 2. The more shells out, the bigger you are. You notice that is an explanation, and I'm not relying on, oh, I just memorized bottom is big. Iodine is big because it's lower on the table. No, your reasoning has to do with this fact of more shells. One other note here while I have this question worded here, sometimes in addition to explaining which one is larger, sometimes they use the phrase here, state and explain. So far what I've done for you is I've done a good job of doing explain, right? Telling me that it's more shells actually tells me iodine is larger. Being 5 shells, obviously I'm bigger than having 2 shells. The part that actually asks you for state, it might surprise you here. State is not just telling me, yep, this one's bigger. State actually means go to the data booklet and actually quote the values. If you actually have the numbers on the data booklet, I want you to quote the number, which means going back to that section 8, which has the atomic radius, or sorry, section 9, iodine has a radius of 136, whereas fluorine is only 60. So stating would be something like iodine, which is, what was it, 130? Bad memory here. 136 and 60. This one here is 136. The units were picometers, whereas fluorine here only has 60 picometers. That's what we mean by state. So be really careful. Sometimes they just say explain. So this bottom part, this explanation region is fine. But for the stating, it's just a matter of going to your data booklet and actually quoting the actual numbers. And with those numbers to support, we can actually see how much bigger iodine having 5 shells is actually larger. So those are the typical styles of questions that you can be worded. They can pick any 2 elements and they can say which is bigger, which is smaller, why, state the values from the data booklet. That trend is fairly easy because I know we have more shells. What about the trend going across? Here's where, like I mentioned, the Z effective becomes really important. The Z effective, even if you subtract off any screening shells, the Z effective goes from, say, a +1 to +2, +3, +4, and onwards to +8. Remember, the Z effective is not the charge that the ion gets when it reacts. This is just the leftover nuclear charge, the leftover positive that hasn't been screened out. And if we couple the Z effective here, couple it with Coulomb's attraction, we know that the radius actually decreases. We wrote this yesterday. Upon any row, my francium or cesium may have been very large. Upon any roll, my radius is tending to shrink. The radius decreases. The language we're going to use is across a period. The word period just means left and right. It's a horizontal row. And when we say across, we assume left to right. Again, for the reasoning, you can't just memorize, oh, I just saw this side here is actually tiny. Your reasoning will be, as you go across, elements have a greater Z effective. They have more positive inside their core that's left over that all the shells can see, which means you have stronger attraction. So that is a reason, not just memorize, oh, this side is small. So stronger, attraction. Right. So we're going to use those fundamental principles of Z effective and Coulomb's law to try to explain the leftover trends. Case in point here, we're going to look at ionic radius as well, but we're also going to use this radius here to actually emphasize the trend in ionization energy as well. So when we do ionic radius, you can call this a new trend here. Ionic radius, exactly the same sort of analysis. It's a little bit hard to measure the distance to the orbital and all that. Let's take the distance of the two centers and divide them in two. But pretty much your ionic radius is the size of the ion, the size after something has become charged. For ions, remember we have two types of ions. This is generally what happens. Metals tend to lose electrons. Again, the fancy word of it is oxidized. If I throw away things that are negative, I'm going to get more and more positive charge. So metals lose electrons to form, the wording here is cations. If you remember cations are positive, whereas nonmetals typically either gain, or even sometimes for covalent bonds, they can share electrons. Again, the fancy wording is going to be called a reduction. We're going to refer to this as a redox reaction in chapter 9. But they gain or share electrons, they get more negatives, and they end up forming anions. Careful, when we were in the electron configuration section, anions weren't that bad. Basically, more people arrive at your hotels. You just put them in the next spot that's available. For cations, we had a special order. You pull them off P first, then S, then D, then F. So let's just have a quick look here. Let's say I take the lithium, and let's say I ionize it. I remove one of its electrons. So that means going from lithium has 3 protons. I'm still going to be lithium, so I'm not touching the core. I'm just coming in with a pair of tweezers. I'm grabbing the first electron that I see, and I remove that. That should remind you of our concept of ionization energy. Ionization energy was this energy, how difficult is it to remove the single electron. When I pull off the electron, the core is unchanged. I'm still 3 protons. But because I've lost the only electron I have on shell 2, I'm not even going to bother drawing shell 2 anymore. I just have the 2 electrons on shell 1, square brackets with the charge, which means I'm now a lithium plus ion. I've been oxidized. That electron is now free to go. So that is called an ionization. Just on that note for ionization, remember to put these have to be all gas, because the amount of energy would be different if it was solids or liquids. It's only correct if you have those gases. In this case here, if I were to ask you to compare the radius, which one's larger? Lithium as an atom or lithium plus as an ion? If you just look at the diagrams here, well, lithium as an atom has 2 shells, n equals 2. Right? I measure all the way out to shell number 2. Having lost that electron made me lose a shell. Now I'm only measuring out to n equals 1. So as a general rule, let's just write down here, generally cations, generally positive particles like this lithium plus, cations are smaller than their parent atoms, than the atoms that they came from. In this example is because we totally lost the shell. I don't have that electron anymore. There's no point drawing out to shell number 2. Lost the shell. Let's say I was beryllium instead. Let's say I had 2 electrons on the outermost shell. Maybe after ionizing, maybe I didn't lose a complete shell, but as I start removing electrons, there's definitely less and less repulsion between the electrons that are on shell 2. So sometimes not even losing a full shell, sometimes it's just less electron repulsion. As I remove electrons, there's now less negative charges to push away from each other because they don't push away from each other as much. Even if I was still on shell 2, I'm going to be a little bit closer to the core, which amounted to, for ionization, it's actually even harder to pull off. So that's the ionic radius here. Let's do the same for, let's say, H. Hydrogen as an atom here. Let's say hydrogen actually gains an electron. Hydrogen is actually a little bit split personality here. Sometimes it can act as a metal, most times, like an acid, but in this case here is actually acting as a non-metal. hydrogen already had one electron. Hydrogen only had one electron. It now is going to gain an electron. I'm going to force an electron onto hydrogen. That electron is going to be added to the next lowest energy spot, and I'm going to end up getting H as a minus. It is possible that you force electrons on so much so that you actually force an electron, the next electron has to go on shell 2, shell 3. You might actually gain electrons, but even in this case here, even from adding just one single electron, I was one shell before, I'm still one shell afterwards, I can still comment that the H minus is expected to be slightly larger. I'm going to exaggerate there with the square bracket with the charge, just to remind me there. The reason for this here is I have that very same proton that's trying to attract my electrons, but in this case here, having squeezed two electrons into this one s orbital together, they don't like each other. They're going to push each other away. They're going to actually end up causing the shell to push out a little bit. Now, there is a little bit of a competition thing, so you could even argue with an extra electron, there's more charge. So if you go F is equal to KQ/R squared, it's true. When you have that second electron, you also have an additional attraction. It's always a fight between, is the attraction more important for the extra electron or the repulsion more important? In general here, anions tend to be bigger, so that tells you that the repulsion, that added repulsion of these electrons hating on each other here is more important than the extra attraction that I get. So generally here, or usually if I form anions, having gained some number of negative charges, depending on how far away I am from noble gas, I can actually memorize, would I be a +1 charge, +2 charge, or -1, -2, okay? But anions typically gain electrons. Usually anions are bigger or larger than their parents. That's not a reason, that's just a general kind of broad stroke. You're going to say because you have more electron repulsion. Having extra negatives, sure enough, there is a little bit extra attraction as well, but usually the negative wins out. You might, in the odd case here, you might even gain a shell, but very weird if the question actually adds enough electrons for you to gain a shell. So that's one way of asking the question here, where you're just saying, compare the ion itself to the parent atom. Now what I can do is I can ask you for a periodic trend for ionic radius as well. You have to be really careful when you're doing this one here. Always be thinking of Bohr model, always be thinking what this thing is supposedly looking like. Let me just see if I can quote some of these values for you here. So I have lithium, beryllium. I'm just going to look over row 2 for you. Boron, carbon, nitrogen. Hopefully I have these in order here. Fluorine, neon, sodium, and magnesium. Okay. So we've done the trend in atomic radius, but let's also do the trend in ionic radius. For ionic radius, we're going to get just the normal everyday charge. Sorry, 1 second here. And when you do that, I want you to actually think about doing it as Bohr models. So for example, I'm going to quote, these values here can be found on section 9 as we did earlier. We have not only the atomic radius, we actually have the ionic radius as well. I just have to pull this up on my other device here. So I have my ionic radius. Let's start off looking at lithium. The ionic radius, the number that was quoted for you here, lithium is a 76. For lithium 1+ as an ion. Beryllium, you don't need to memorize these are on the data booklet, 45 for the 2+ ion. The boron, if it was a 3+, I know boron is sort of a metalloid, it doesn't really want this positive charge, but it's a 27 for a +3 ion, all the way to carbon, which is 16, right? No real surprise there. We expected, well, as you go across, 3 protons, 4 protons, 5, and 6, gaining more protons means the Z effective is greater, of course smaller. But here we get to a problem. Nitrogen actually has an ionic radius of 146. Well, what gives? I thought the radius was supposed to be decreasing as you go across. If you look very carefully, however, you'll notice if I did the Bohr model, lithium +1, I used to be 2 shells. Having lost that electron, I'm now 1 shell. Beryllium used to have 4 electrons. In becoming the +2, I've also lost a shell. So we're talking about these 4 are all just 1 shell, n equals 1. The charge for the nitrogen ion that they gave you is actually nitrogen 146 is actually for the -3 ion. Nitrogen does have the 2 shells, so nitrogen by itself looks like this. And when nitrogen gains those electrons, experiences that extra electron repulsion, that ends up pushing the shell here even further out. So in that case there, when I actually add electrons, first thing, we're not just measuring out to one shell. The one shell might also be very tiny, like the 16 or the 27, but we're measuring the distance to the second shell. Of course, the second shell is going to be bigger than the first shell. So be really careful when you look at these ones here, especially when you cross over from the positives from the earlier row to this one here, nitrogen -3, oxygen -2, fluorine, and neon. These ones here are all actually talking about n equals 2, measuring to 2 shells out. No doubt those numbers here are actually larger, although 146 drops to 140 for the oxygen -2 ion. For fluorine, it drops to 133 for the -1 ion. And you'll actually find that we don't have an ionic radius for neon. Hopefully you know the answer to that. You can also compare it to, let's say, the sodium and the magnesium. Back in the metals, we would expect to be positive again. Sodium for the positive one, let me just quote the number. This is 102 as a positive. Magnesium is now going to be 72 as a positive 2. That one there, even up to aluminum, which is a +3, those ones here are also talking about n equals 2. So yes, in general, the atomic radius trend still works. As you go across, you pick up more protons. There's not any great dramatic difference in shielding. So the more protons in the core, your shell gets tighter in. But especially every row will have a crossover value where some of the elements, we're talking about the earlier shell, and then whenever you switch over to the anions, we're now talking about Bohr models that actually have one extra shell. Once I jump to that shell, there's going to be a big difference here, but at the same time, it would decrease as you go across. You'll find that with some of these here, let's just pop down to germanium here. Germanium actually quotes for you 2 values. When germanium is a +4 ion, it actually has a radius of 53. When germanium is a -4 ion, it actually is a 272. We get that same notion. When it's positive, it's probably lost some shells. When it's negative, it's probably talking about the outer shell. Be careful when you're making that comparison. If they do specify the actual element, you can actually do your configuration stuff, figure out which electrons you've actually lost to actually figure out what happened. So case in point here for germanium, I'm just going to do the connotation for you here. Argon 4s2, 3d10, 4p2. Double check that. That's just plain old germanium. If I became the +4, I need to remove electrons p first, so those come off first. I don't remove the d's just yet. I remove these ones. You'll notice I've lost the SMPs. I've lost the valence shell. So if I compare it to the parent atom right above, the radius here was actually 120. Having lost the p's and the s's, having lost the orbitals that are like dumbbell shaped and really far out, or the circle shape here, and just having the butterfly, these d orbitals that are held really close to the core, my radius is significantly smaller than the 120. Different scenario here when I become the -4. Take that same configuration, I would have been a blah 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 4s2, 3d10. Instead of being 4p2, I'm now going to be 4p6. I have the same number of protons. I'm still germanium, but having those 4 extra electrons actually pushes further out. I still have the valence electrons, so I should still be roughly like 120. And in fact, that added repulsion, I'm still going to be, let's say, roughly 4 shells out, but having those extra 4 electrons squeezed in next to germanium, which it doesn't really like, it's going to actually push out those same 4 shells, but germanium as a negative ion actually is going to be much farther, much larger out from there. Again, these numbers here, you can just look on the data booklet. You don't need to memorize them, but that's how you do with ionic radius. Remember, when you're explaining, either draw the Bohr model, either refer to Z effective. Don't just tell me, I memorize this side is small, I memorize this side is big, and also try to avoid that term 8. Okay. One last trend for today. We'll leave the other 3 for tomorrow. The last trend is a guy that we already visited in chapter 2, which is this notion of ionization energy. A favorite question of theirs, a nice hint for your test here, is define ionization energy. Try it out for yourself. Make sure you can do it. See how you did here. Ionization energy is the minimum energy needed to remove an electron. We've been seeing this since chapter 2. It's coming in with the pair of tweezers. It's grabbing that first electron that I see and trying to remove the electron. So, because layers of an onion, I can only pull off the outermost shell first. I'm going to try to remove this electron first. Minimum electron, you need this word here, minimum. This question would usually be out of 2. So far, it's only 1 out of 2. you need to emphasize here, if you just did that to one single atom, it's really, really tiny. What I'm going to do instead is I'm going to line up a whole Avogadro number of these atoms, and I'm going to imagine pulling off this very same electron off every one of these atoms. So that's why in the technical definition, remove an electron from, you have to mention a mole. You're not just doing it to one atom, and it has to be gaseous. I'm just going to use a generic word here, species, because especially when you ionize multiple times, they're not all neutral atoms to begin with. They become more and more charged. The representative equation, another favorite question of theirs on the test. Whenever people see equation, they start thinking, oh, what math and what numbers do I want? When they say representative equation, they just want a balance equation. So if I were the metal M, I need to emphasize that we're in a gas state. And if I got first ionized, the first time you come in and you remove my electron, my protons are intact. That's what makes me element M. So M is still intact. But having lost that electron, I'm now going to be an M plus charge. This one here will similarly be a gas, and now that electron is free to go. There's going to be a number to this here. I'm going to show you the table in a second. But 10, usually they'll just say kilojoules, but it is understood because we are doing it for an Avogadro number, it's understood as kilojoules per mole, even if I don't put that mole there. Okay? So that's the representative equation. That's your ionization energy. What we're interested in for this chapter is to figure out what's the trend going across the periodic table. In this case here, we're actually going to use radius as a trend. So far, I'm thinking of my periodic table. We knew from our radius trend, things tend to get bigger as you go down like this. Things tend to get smaller going down like this. As you think about a Coulomb attraction, let's see if you can quote for me, right? So Coulomb says F is kq over r squared. Let's see if you can quote for me, what do you expect to happen to the ionization energy as you go down? Any group, doesn't have to necessarily be group number 1. Does it increase or decrease? And in a similar fashion here, what happens to the ionization energy going across, assuming that we're reading left to right? So ionization energy across period. Think about the size. Think about the protons trying to hang on to the electrons. Ionizing is trying to fight against the atom, is trying to pull the electron off the atom itself. Okay. So let's go up and down a group first. Should be a little bit easier. When I have a large atom like cesium, like francium, pulling this electron off, it's actually really, really far away from the core, as opposed to pulling off, let's say, for hydrogen. The effective nuclear charge may be +1 in all these cases. Yes, francium has way more protons, but by the time you subtract out all those screening electrons, this outer row only sees a +1, like hydrogen has a +1. The only difference, though, is even though the Z effective, even though the charges remain similar, you notice that having way more shells means your radius is bigger, my separation distance is big, meaning the protons are really having a hard time holding on to that electron. You come in with a pair of tweezers, a quick bump of it, and this one here is gone. So really easy to remove. We would say low ionization energy. This one here should be high ionization energy. You really need to pull on it, forcefully get it going. So ionization energy down a group, we would say it decreases. It becomes easier. Okay. Again, you need an explanation here. You cannot just say, I memorized it. The bottom is actually lowest. In this case here, you have to refer to, well, we know that at the bottom, we have big radius. And when you have big radius, reason for big radius is because you have more shells. When you have big radius, we have less attraction. That is an explanation. How about the ionization energy going across? As you go across, we saw Z effective. That principle become more important. As you go across, we're all the same energy shell. So far, this looks like, let's say, energy level 3. We're all going to be 3 shells out. But what's happening here is, as I step across, I'm going to gain protons in the core. The more and more positive the center is, the higher the Z effective going from +1 to +2 to +3 and so on and so forth, the higher the charges would actually increase the attraction, increase the hold your nucleus has on your outer shells. If I have 3 shells, I'm going to end up pulling those 3 shells tight to the core, which means when you come in forcefully and try to remove these electrons, I'm not going to actually have a really loose hold on that electron. I'm going to fight against you really hardly. So in this case here, a higher ionization energy whenever things are small. So higher ionization energy here, we can say the ionization energy actually increases. Again, in terms of your explanation, you're going to use the terminology. It's because going across, the Z effective increases. You have a greater leftover charge even after you worry about the shielding of electrons. So that's our trend for ionization energy. They actually like asking this question as an evidence. How do we know that they're subshells? In this case here, for evidence of subshells, let's take, I think we did sodium as an example before. So sodium, let's just do our configuration. We did this a little bit in chapter 2. So sodium as a Bohr model look like this, right? 2, and then we have 8 on this shell here. Remember, electron arrangement is just saying 2, 8, 1. It's just a listing of how many electrons I have on each shell. Basically, what I'm going to do is I'm going to start ionizing it. I'm going to come with a pair of tweezers, and I'm going to figure out what the ionization energy actually is. So here's my ionization energy. This is sort of, again, which ionization, how many times I've come in for an electron. Relatively speaking, this first electron should be really easy to pull off. This is the one that's farthest out from the core. Coulomb says the bigger separation distance, I don't have a really strong attractive force. So that first ionization energy, really, really easy. Second ionization energy, I'm noticing that I'm actually reverting down a shell. I've lost that first shell. I'm grabbing one of these electrons on shell number 2. Right now, it's actually enjoying full gas stability, like a noble gas. So it's really going to fight against me. After having lost 3s1, it really doesn't want to lose this 2p6 and make it a 2p5. So what's going to happen, it's not impossible, but maybe my number goes from 10, and maybe I suddenly go to, I don't know, 1,000. Okay? The second electron is a lot higher. Now all the electrons afterwards, when I successively ionize, I expect it to get harder and harder, because first thing is, as I keep removing electrons, all these other electrons are going to be on row number 2. But unlike what the Bohr model suggests, where all these electrons look equidistant from the core, I had to think about the electron configuration model. So far the electron configuration model, so far at 2p6, I really am resisting you. I don't want to actually lose that electron. I have full gas stability. As you remove that one, it's hard. As you remove the next one here, it's also shell 2, also hard, a little bit harder. The next one we did as an exception in chapter 2, this one here actually ended up being easier. If you remember, by losing oxygen's electron, we end up getting that half field stability. We might actually end up getting, this one's harder, but the next one out from there actually is a little bit easier. So depending on the actual subshells that I'm looking at, when you actually do this on your lab, you actually see that this graph here actually zigzags back and forth. There are exceptions depending on maybe the odd half-filled stability, maybe the odd difference between pulling off a P versus an S. Because this one here isn't a nice linear increase, that's actually evidence for the fact of having subshells. That means electrons on shell number 2 are not all equidistant. Once you removed enough for 8 electrons, as you now start coming in and trying to remove electrons from the first shell, those again will significantly be harder than earlier. This is so far from n equals 2. When I get to that, what is it, the 9th electron, it's going to be shell number 1. That again will have a significant jump. Wherever it takes a leap, we know we've probably lost the shell. Okay. So hopefully that fleshes out a little bit more with radius and ionization energy for you here. Very little of it is tested on the chapter 2, but at least we see it with periodic trends here. Let me give you a quick summary of these trends so far. Really handy of having the periodic table organized in this fashion. We're going to start off just with metallic nature. Okay, so metallic properties increase as you go in that direction there. One of the reasons for that here was the radius generally increases. Remember to come with it for a reason. For the reasons for these ones here is because going down, we have more shells, or going to the left. Notice I'm not going across a period to the right this time. More shells actually means it also means less Z effective as you go to the left. And in that case there, the larger the atom, if you think about trying to ionize it, the larger the atom, the easier it is to ionize. So if I point the general trend in the same direction, your IE actually decreases. It gets easier to remove. Translate that for yourself. Easier to remove the electron because the radius is bigger. Okay, so radius and ionization are opposites of each other. They're inversely proportional. Tomorrow we'll come back and we'll study 3 other trends. Thanks, guys. If you have any questions, just let me know. Take care.